Hi everyone, this is Group 13 and this is our final presentation. There are 5 members in our group and our topic is Tune Your Mood, personalized stress relief music created by AI prediction. Our presentation consists of 4 parts. The first part is the introduction of music therapy. The second part is the motivation of our project. And the third part is the implementation steps and details. And the last part is the prospect of this project. As we all know that music therapy is very popular nowadays because music therapy can promote wellness, manage stress, alleviate pain, express feelings, and promote physical rehabilitation. However, music therapy is problematic because of 4 reasons. Because usually doctors choose improper music genre for the patients, and the therapy is not consistent. And the therapy is often prescheduled and thus lacks flexibility, which is crucial for psychotherapy. And music therapy is often lacked of personalization. And this is our implementation steps, which is divided in 2 blocks. The first block is to train a model that can predict the stress level of the patient. And the second block is to generate music with AI for the music therapy.
So the first part we show about the stress level and habit evaluation. And the dataset we choose to use is the music listening histories dataset. The below is our future engineering. Time and step. Date and time when form was submitted. And the respondent's age. Hours per day. Numbers of hours the respondent listen to music per day. While working. Does the respondent listen to music while studying or working? Instrumentalist. Does the respondent play an instrument regularly? Composer. Does the respondent compose music regularly? Foreign language. Does the
So to complete part 1's stress level prediction, first step is to import data sets from CSV file. The dataset is the music listening histories dataset. So after import the dataset, we convert the text to numbers so we can use for future use. And we weight the sum of the proportions of various music like hip-hop music, K-pop, Latin or R&B music, and we use it for input X.
Next, let me present what model we will use. The type sum number can be thought of as an input x2. The varied music BPM can be thought of as input x1. And the score of N6T can be thought of as output y. Hence, we will try 3 classification methods: random forest, decision tree, and support vector machine, and 1 simple regression, linear regression. Here are the results of using a support vector machine. In the beginning, we consider type sum and BPM as variables that can be treated as a plan for classification. However, after experience, we found that the accuracy is about 12% and MSE is about 14%. Here are the results of using a random forest. In my opinion, since the support vector machine classification method can be used, Random forest and decision tree can also be used theoretically. However, the experience results of random forests are not much different from those of support vector machine. The accuracy is about 13% and MSE is about 13. Here are the results of using decision tree. The accuracy is about 10% and MSE is about 14. Here are the results of using a linear regression. I suddenly realized that the output is a numerical value, and I have decided to use linear regression. We found that the accuracy is about 9% and MSE is about 8. Using linear regression can make the MSE lowest. Let me jump off conclusion.
Okay, so from previous slides, we can know that music therapy is a complex problem. So it is not appropriate to use the traditional classification techniques to choose music for the patients. So we have proposed a generative music model to solve the problem. The first step of our model is data preparation and extraction. In this step, we first mount the Google Drive, and the script uses Google Colab and mounts Google Drive to access the data stored in the Google Drive. And the next step is to unzip the dataset. The dataset is presumably to be a collection of music files, and it is stored in a zip file. This part of code unzips the dataset into a specified directory for processing, and then it checks the contents to verify the extraction. Next step is feature extraction. We utilize the PyDub and Librosa library. We first install PyDub, which is a library for audio processing, and then we import Librosa for audio analysis. In our convert and extract features function, this function is aimed to process each audio file in the given folder. We process by converting the .au file format into .wav file format. And then we extract the features with Librosa library. The Librosa library is used to load the WAV file and extracts the MFCC, which is male frequency substrate coefficients in phoneme, and it is a common feature used in audio and speech processing. We also implemented a technique called feature aggregation. This technique calculates the mean of the MFCCs across time to create a single feature vector for each audio file. And our next step is model training. The first line of code is data preprocessing. We first normalize the extract feature using a function called standard scalar and reshapes the size to fit the LSTM network's input requirements. And then we split the dataset into training and test dataset. And then the model creation of LSTM constructs an LSTM-based neural network using Keras. And the last part is model training, which trains the model on the training data for fixed numbers of epochs. And the next step is music generation. in the generate music function. It generates new music data by feeding a seed sequence into the trained model and iteratively predicting the next step in sequence. We finally save the generated sequence, which is a NumPy file. And since the generated file is a NumPy file, so we have to implement a DSP project to convert it back to audio. So in this NFCCS to audio function, it converts the generated NFCC sequence back into an audio signal, and it involves approximating the male spectrogram from the MFCCs. And converting it back to audio signal would use the STFT, which is short time Fourier transform. And then the algorithm we use is called the Griffin-Lim algorithm, which is used to reconstruct the face. And lastly, we load and process the generated sequence, which we load the generated sequence from the saved numpile and then convert it back to audio. And in the last line of code, the generated audio is a WAV file and it is saved to the Google Drive. In our model, we use the LSTM method, and LSTM is divided into 3 gates. The first gate is forget gate, and second gate is input gate, and the third gate is output gate. And in the forget gate of LSTM, it determines whether the memory from the previous time step should be retained or forgotten. What this means is the component of the LSTM does this by looking at the previous hidden state, ht minus 1, and the current input x of t, and then it outputs a number between 0 and 1 for each number in the cell state c t minus 1. And a value close to 0 means that to forget this completely, and a value close to 1 means to keep this entirely. So the equation in this slide, C of t, represents the new cell state being an element-wise multiplication of the forget gate's output with the old state, and it adds the input gate's output with the candidate value C of t, with the curly thing on top, C of t, which are the possible new values to add to the gate. And the input gate is used to regulate the amount of new information entering the memory. In this gate, the function the I of t function is a sigmoid layer that takes the previous hidden state ht minus 1 and the current input x of t, and it applies to the weight w of I and adds a bias term b of I, and it also outputs a value between 0 and 1, because since it is a sigmoid function, so the output is 0 between 0 and 1. And the next function is the C of t function. The C of t function is a 10h layer that also takes ht minus 1 and x of t, but it applies a different set of weight w of c, and also adds a different bias b of c. It outputs a vector of new candidate values. It is scaled between minus 1 and 1 because it is a 10h function. These candidate values are proposed updates to the cell state and are modulated by the output of the input activation. And last gate is the output gate. The output gate decides what the next hidden state h of t should be. Or in other words, it generates new output based on the current input and memory. In the equation O of t, which is also a sigmoid function, so it outputs a value between 0 and 1. And the other function is h of t, which is a tanh function. The tanh function defines the output, while the sigmoid function, the O of t, decides which parts of the cell state to output, and then the result is filtered by the output of the tanh function. So what it means is the input first goes through the sigmoid function, and then it goes through the tanh function, and then the output is generated by the concatenation of the two functions. So in summary, the three gates, the forget input and output gates, covers the main components of a LSTM cell. And each of the gates contributes to the cell's ability to remember and forget information over time. And this is done by the sigmoid and tanh function. So these two functions are very critical in processing sequences for tasks like language modeling, time series analysis, or etc. And I would like to talk about the problems during our implementation. The first problem is during the process of audio conversion, which is the process of converting NumPy file to WAV file. We have found out that the DSP process would occur quality loss due to the method and technology we are using. Since converting audio from one format to another can result in a loss of quality, so we have to be careful of this. And why don't we use JN model? Because first, JN is notoriously difficult to train, and JN is also more potential for bias when it comes to generating music or audio processing. And also, JN is limited of it's hard to interpret the process of JN because JN often works like a black box, so it is usually difficult to debug and understand what the JN training model is doing. So in our approach, we choose to use LSTM with a mixture of VAE, which we incorporated the LSTM into the encoder and decoder of the VAE model.
Exploring the potential market for music therapy reveals three promising prospects. The first one is personalized music therapy, and the demand for personalized healthcare and well-being solutions is growing. Personalized music therapy can cater to specific mental health, emotional, and cognitive needs to individuals. The second one is broader market applications. This approach broadens the market reach, including sectors such as corporate wellness, stress management programs, and general public engagement. Music therapy can be integrated into diverse environments to enhance overall well-being. And the last one is educational and research applications. Educational institutions can benefit from integrating music therapy into student programs for improved focus, creativity, and emotional well-being. Additionally, researchers may explore the therapeutic effects of music in various fields. Each prospect presents unique opportunities and challenges. Personalized music therapy aligns with the increasing demand for individualized well-being solutions. Broader market application offer versatility, while educational and research applications contribute to the scientific understanding of music therapy's impact. A comprehensive strategy that considers these prospects could lead to a successful market entry and growth in the field of music therapy.